Hi, everyone. So I'm slowly learning about technology. If coronavirus ends up taking me, there will at least be a permanent record of my technological ascent in some sense. So there's one more thing I'm going to use during this video that will involve screen mirroring my iPad and using that as a whiteboard instead of the one that's native to Zoom itself. But I figured kind of a low bar for that would be for me to finally complete these videos I started sometime back on the Catalan numbers. I did the first three. At the time, we had kind of managed to find a formula for the Catalan number generating function. All three of those videos are on Canvas, and I've also put those on the YouTube playlist for this class. But right now, I want to go ahead and actually share my screen with you, and we'll do that. We'll play with that. Here we go. All right. So just by way of review, here's what we knew about the Catalan numbers. And remember, we define the Catalan numbers via just the number of ways to parenthesize or multiply together in fixed numbers. You could have also talked about adding those numbers together, and by the way, you leave the numbers in place. You don't commute them around or anything like that. Okay, and the recurrence relation that we ended up deriving was that the nth Catalan number is given by this sum of products of prior Catalan numbers whose subindices actually add up to n. Okay, so the number of ways to parenthesize in numbers, well, you can either have the first number parenthesized off by itself and the last n minus 1 parenthesized off, and you count the number of ways to multiply those together. Or you could parenthesize the first two numbers and the last n minus 2 and use the previous Catalan counts to count the number of ways to multiply those together, etc. And of course, C1 is equal to C2 is equal to 1. Okay, one number, well, I mean, there's only one way to parenthesize those, same thing with 2. And we also discovered in those previous videos that the Catalan generating function, which I've written right there, satisfies the identity that if you square it, you just get the same thing right back, but you have to get rid of the x term. And then in the third video, we actually use that fact to come up with a formula for the generating function. And there it is right there. We found out that the Catalan generating function is 1/2 minus 1/2 times that square root times the square root of 1 minus 4x. Okay, so in general, when you have a generating function, you can use that to extract the nth coefficient, and sometimes that will give you a nice formula, and eventually we're going to be able to do that. But the problem is that generating function, we don't really know how to handle that just yet. We have some generating functions in our back pocket from back in chapter 6 that we got pretty comfortable using, but we don't really know how to handle like a weird square root like that. Okay, and we had the donut functions, we had all manner of things that involved manipulations of geometric series, but we haven't been able to handle that yet. So I want to talk about that a little bit. Okay, so let's go to another board here. All right, so how do we handle generating functions in general? Okay, so these are GFs in general. Okay, how do we handle them in general? Well, like how do we find like a formula for a generating function? Well, so suppose that f of x is equal to a0 plus a1x plus a2x squared plus etc. Okay, and f of x is just some other function, but I want to write it as a power series polynomial in this way. You may recall from Calc 2 that the way you do it is you basically plug 0 into the function to get a0. So notice that like a0 would have to just be the function evaluated at 0. How would I get a1? Well, I take the derivative, all right? So f prime of x is equal to a1 plus 2x squared, or 2a2, okay, 2a2 x to the first power plus 3a3 x squared plus etc. Okay. And of course, we see that a1 is therefore f prime evaluated at 0. Okay. And how would we get like a2, you know, and continue to get these various coefficients that would allow us to be able to write a function or be able to write a coefficient for a power series representation for a function using the function itself? Well, okay, I would have to take a second derivative. So like f prime prime of x is equal to, what's that equal to? Well, it would be 2a2 plus 3 times 2. Okay, so don't multiply things out and destroy a pattern here. 3 times 2, a3x plus etc. Okay? And notice this time we see that a2, like if I plug in 0 for x into the second derivative, it's going to kill everything after the the a2 term, but that you would have 2a2. So actually a2 is equal to the second derivative of this thing. The second derivative of this thing evaluated at 0, but then I have to divide by 2, but really what that is 2 factorial. 2 factorial. And of course, going up to the previous guys, we realize, oh man, a1 was really the first derivative at 0 divided by 1 factorial, when you think about it for a second. And a0 was kind of like the 0th derivative divided by 0 factorial, if you will. Okay. So a0 is the 0th derivative evaluated at 0 over 0 factorial. A1 is the first derivative at 0 over 1 factorial. A2 is the second derivative evaluated at 0 over 2 factorial. And we see the pattern here. Okay, so let's go to next one. So if I want to write f of x equal to a0 plus a1x plus a2 x squared plus etc., then an, this is a pretty famous formula for the so-called Maclaurin series representation of the function f, which is just the Taylor series centered at 0. Okay, you would take the nth derivative, which I mean I'm not going to write in primes. The Newton notation is to put in parentheses. That means take n derivatives. The nth derivative of the function evaluated at 0 divided by n factorial. Okay. Okay. Why am I talking about this? Well, first of all, I know you might be sort of shaky in remembering this, even though it's a Calc 2 thing. I understand. I mean, this stuff kind of drifts into the back of your cognition. So I wanted to review that, but also what I wanted to do was apply it in the example of a binomial where the power is no longer necessarily an integer. Okay, so let's do a little example here. So what if f of x were like 1 plus x raised to the alpha, where alpha is not necessarily an integer, okay? Okay, so if I wanted to represent this as a power series, you know, what would I have to do? Well, okay, so A0, what would A0 be? A0 would be this thing evaluated at 0 over 0 factorial. So A0 would be, you know, A0 would be 1. Okay. What would A1 be? Well, A1 would be the derivative of this thing. So it would be F prime evaluated at 0 over 1 factorial. Okay, which, what is the derivative of this thing? Well, it's, you know, alpha 1 plus x to the alpha minus 1 evaluated at 0. Okay, so it's going to be alpha, and incidentally, the chain rule would have to technically be applied, but the derivative of the inside here is just 1. So it would just be alpha over 1 factorial. Okay, and let's see here. Let's get another page to work with here. What would A2 be? Okay, or yeah, what would A2 be? So A2 would be the second derivative evaluated at 0 over 2 factorial. Okay, well, if I take the second derivative of that thing, so going back, if I take the second derivative of that thing, it's going to be alpha times alpha minus 1, okay? Alpha times alpha minus 1, so let me just kind of write that down. The second derivative of this thing evaluated at x is just alpha times alpha minus 1 times 1 plus x raised to the alpha minus 2. Okay, so therefore A2 is going to be alpha times alpha minus 1 divided by 2 factorial. And do you see a pattern starting to emerge here? What do you think A3 is going to be? Well, it's going to be alpha, alpha minus 1, alpha minus 2 over 3 factorial. And then you start realizing, oh man, I do see a pattern. Essentially, A sub, you know, A sub whatever, A sub n is going to be a product of like falling, it's like a falling product starting from alpha, where I have a total of n terms. It's that Pochhammer symbol that we talked about a while ago. It's kind of like alpha put in. Yeah, alpha put in is what that is. Okay, so incidentally, we call this, you know, alpha in parentheses sub 3 divided by 3 factorial. And that alpha in parentheses sub 3, that's the Pochhammer symbol. That just means that you start at alpha and you decrease by 1 each time, and you have a total of 3 factors in the product. Okay, so like this guy up here, A2, that's just alpha in parentheses sub 2 divided by 2 factorial, if you will. Okay, and in general, an is just going to be alpha sub n divided by n factorial. Okay, so it's going to be the falling factorial alpha, you know, with n terms in it, the Pochhammer symbol, alpha sub n divided by n factorial. Okay, so what does that mean? Well, let's get another page here. So if f of x, so what that means is that 1 plus x raised to the alpha is equal to, is equal to what? Well, it was 1 plus, okay, alpha, you know, let me just write it here. It's alpha sub 1 over 1 factorial x plus Pochhammer symbol alpha sub 2 over 2 factorial x squared plus alpha Pochhammer symbol sub 3 over 3 factorial x cubed plus etc. Okay, so that's a 3 right there, sorry. Okay, and if you know, if you want to be able to write this succinctly, this is x to the first power, you just define, we could define the Pochhammer symbol alpha sub 0. That's just by definition. That's by definition equal to 1. Okay, and so then we can actually write 1 plus x to the alpha as being the sum n going from 0 to infinity, you know, alpha Pochhammer symbol sub n factorial x to the power n. Okay. We're not going to really concern ourselves with convergence at this point, but that's just the formula that we have, right? So, and we could figure out the radius of convergence if we wanted to. And by the way, this formula actually works even if alpha is an integer. Watch this. Okay, so for example, let me just kind of go to a 6th page here. Here's a 6th page. Okay, so watch this. Here's for example, what if I had, you know, 1 plus x to the 7th power? Well, what would this be? It would be sum n going from 0 to infinity, and you would go 7's Pochhammer symbol n over n factorial x to the n. Okay, and what's interesting here is what is 7 sub n? Well, look, I mean, once I get up to 8, that thing is right. So watch, what is 7 sub 7 equal to? Think about that. Okay, so for example, what is 7 Pochhammer symbol sub 7? Well, it would be 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 7 factorial. You know what I mean? That's 7 factorial. But then 7 sub 8, okay, or 7 sub anything actually, 7 sub n is equal to 0 if n is beyond 7. Okay, if n is beyond 7, you just get 0 from that point on. That's interesting. So really, this is just a finite sum. Okay, so this is just the sum n going from 0 to 7, 7 sub n over n factorial, and then it's x to the n. Okay. Yeah, and what's interesting here, okay, so let me actually go to another page to show you this. Let's think about what is 7 Pochhammer symbol n over n factorial actually equal to? Well, that's 7 times 7 minus 1, dot, 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 right, dot, 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 and it's going to be 7 minus n plus 1 all over n factorial. Okay. And what is that? Well, I could complete the factorial by multiplying and dividing by 7 minus n factorial. And then this would be 7 factorial over n factorial, 7 minus n factorial. Okay, which is 7 choose n. 7 choose n. That's what that is. And therefore, if I kind of look back at the previous page right here, that right there is 7 choose n. Like, okay, back over here, we just found out that this is 7 choose n. That's amazing. So if I go back to this guy over here, what is this? Well, this is just equal to the sum n going from 0 to 7, 7 choose n, x to the n, which is exactly what we already knew from the binomial theorem with integer powers. Okay, so this thing just verifies what we already knew for integer powers, but it's extended it to non-integer powers, if you will. Okay, yeah, okay. So that's interesting. Okay, so again, I want to go back to this thing right here and kind of have this be the last thing that we look at here. This equation right here is exceedingly important. This thing right here is the one that we are going to need to kind of finish our exploration of the Catalan number stuff. Okay. So yeah, that is interesting, I think. So we're going to take that and we're going to use it to actually finish off our exploration of Catalan numbers. Bye for now.